Is it on?
So when is it on?
Okay, so Nicole Schweikardt is going to tell us about locality from circuit lower bounds.
Okay, so first of all, I would like to thank the organizers for giving me the opportunity to present these things here. So it's on locality from circuit lower bounds. Stephen already gave a very nice introduction to locality results, and we will take a closer look at this Geifmann locality or isomorphism locality, which was the first kind of locality discussed in Stephen's talk. Okay, so in this talk, I will consider finite structures only, but most of the time I will consider finite graphs. But whenever I speak of a finite graph, you can also think of a finite relational structure. So everything that I formulate for graphs here also works for finite relational structures. Okay, and I speak about graph properties and graph queries. And a graph property for me is something that's closed under isomorphism. So P is a graph property. If whenever two graphs are isomorphic, then they either both have this property or none of them has this property. And the same holds for queries. So a k-array graph query associates with every graph a set of k-tuples of nodes of this graph. And we require that such a query is closed under isomorphism. That means if G and H are isomorphic graphs and pi is an isomorphism from G to H, then for all k-tuples A that belong to the query result when the query is applied to a graph G, then if we map A by the isomorphism to the tuple pi of A, then this has to belong to the query result for the isomorphic graph H. So graph properties and graph queries are closed under isomorphisms. Now, classical logics like first order logic or least fixed point logic or whatever logic is your favorite logic, they allow us to express graph properties or graph queries in a very natural way. Like first order logic, this first order formula here says that node X of a graph lies on a triangle. So there are nodes Y and Z such that there is an edge from X to Y, from Y to Z, and from Z to X again. But the drawback, if we look at these logics like first order or least fixed point logic, they are too weak to express some properties that are computationally very easy. So like parity of the universe or parity of the number of edges of a graph cannot be expressed by LFP. On the other hand, if you go over to more expressive logics like second order logic or existential second order logic, you can also express properties that are really hard, like NP-complete problems. So what I want to do in this talk here, I want to extend first order logic in such a way that it still can only express computationally easy problems, or everything that you can express can be computed easily, but in a way that really extends the expressive power of first order logic. And that's what we're going to do. We're looking at invariant logics, and the most basic kind of invariant logic that I will take a look at here is order invariant logic. And then, so I'll first introduce these invariant logics, and then we will look at non-expressibility results for, in particular, version of invariant first order logic, and I'll close with some final remarks. And in this part here with non-expressibility results, I want to show in detail one particular proof to you, which shows a locality result not by Ehrenfeucht-Fressé games or by classical methods like compactness, but by using lower bounds from circuit complexity. Okay, but let's first have a look at what invariant logics are. And we already had a couple of talks in this workshop speaking about invariant logic. So the idea is we extend the expressive power of a logic by allowing formulas to also use arithmetic predicates, like a linear order on the set of nodes of a graph, and maybe also the addition that fits to the linear order and the multiplication and whatever arithmetic predicate you like. So for this, when you have a graph with a vertex set V and a linear order on this set, you just identify the vertices with an initial segment of natural numbers. So with the numbers 0, 1 up to n minus 1 if n is the size of the vertex set. But if you do this, you can also express queries that are not graph queries anymore. So you could say the first vertex is red or has a self loop or something like that. But referring to the first vertex is something that isn't a graph property anymore. So to ensure that your formulas only define graph properties, you require formulas to be independent of the particular way the order is chosen. And you can formalize it like this. So if you have a first order formula that speaks about graph and a linear ordering, then this formula is called order invariant on a graph G if for any linear order and any other linear order on the vertex set of the graph together with the first linear order satisfies the formula if and only if the graph together with the second linear order satisfies this. And Albert in his talk earlier this week already gave a description of one motivation from database theory, why order invariant formulas are something natural in some sense, because you want queries that are posed against databases to be just dependent on the logical view of the database. But on the other hand, your database is stored on some disk, and this means the elements in the database are stored in some linear order. And why not give your query language the opportunity to use this linear order? And that's exactly what order invariant first order logic does. You can use this order, but the query must ensure that the query result doesn't depend on the particular linear order, which means it doesn't depend on the particular way the database is physically stored on your disk. And now if you allow a formula to use the linear order, why not allow it also to use arithmetic on these numbers that the linear order associates with your vertices of the graph? And that's what you do with addition invariant first order logic. So addition invariant first order logic means I look at a formula that speaks about a graph and that uses a linear order and a ternary predicate for addition in such a way that whenever you have two linear orders and the associated addition for these linear orders, the graph together with the first linear order and the addition satisfies the formula if and only if it satisfies the formula with respect to the second linear order and addition. And you can also add addition and multiplication, then you get addition and multiplication invariant first order logic, or, and that's what I will have a look at most of the time in this talk, you can add all numerical predicates that are there. So your formula is allowed to use all kinds of numerical predicates, and a formula is called ARP invariant. ARP stands for arbitrary numerical predicates. If, well, it doesn't matter which kind of predicates you use or how you embed your structure into an initial segment of the natural numbers. Okay, so that's the setting we look at, and let's have a look at a couple of examples. So here is an addition invariant first order formula that expresses that the number of vertices is odd. So the number n of vertices is odd. This means that, well, the universe is associated with numbers 0, 1 up to n minus 1. This means that the maximum element in my universe has to be even, and that's what the formula says. There exist numbers x and z, such that z is the maximal element with respect to the linear order, and z is an even number. And if you use addition and multiplication, then you can in a similar way express that the universe, the size of the universe is a prime number, also in a way that doesn't even use the edge relation of your graph. And in this way we obtain that, well, what do we see? Addition and multiplication invariant first order logic is strictly more expressive than just addition invariant first order logic. Why? Because you can't say that the size of your universe is a prime number by just using addition. addition invariant first order logic is strictly more expressive than just order invariant first order logic, because you cannot express in order invariant first order logic that your universe is of even size. And well, on the other hand, what we also easily see that ARP invariant first order logic can express some undecidable properties, like add a unary predicate that consists, or that's a set that's not decidable, and then your formula can express undecidable things. But what we also know is that order invariant first order logic is strictly more expressive than plain first order logic. And seeing this is a bit more difficult than just looking at such easy examples. And there is one result by Martin Otto, and originally things were, so a different example was observed by Gurevich, but Martin Otto gave this example that I have here at the slide, and it says that under graphs that have a particular shape, connectivity can be expressed by order invariant first order logic, but only on special graphs. So what does this theorem say? There is a finite relational signature tau, which contains a unary relation symbol u and a binary relation symbol e, and some other relation symbols that we don't care about here. And there is a first order, so plainly first order definable class of finite tau structures, such that on this class, connectivity of the graph, the induced subgraph, is defined by the edge relation E on the set U, is definable in order invariant first order logic, but not in plain first order logic on this graph C of class, on this class C of graphs. And the overall idea that is built in this class C of graphs is that your structure that belongs to C in some sense encodes the entire Boolean algebra on the nodes that are interesting for the connectivity here. Sorry? So C here is not a class of graphs, but a class of finite tau structures, so graphs with some other relations on them. And inside such a structure, I look at the graph defined by the relations U and E. And I don't want to go into details here, so in Leonid Lipkin's textbook, you find in one of the examples a detailed description of what the structures look like. Okay, so what else do we know about the expressiveness of invariant logics? So least fixed point logic on ordered structures precisely captures polynomial time properties of ordered structures. And this means order invariant least fixed point logic precisely captures the polynomial time computable graph properties and queries. So it seems like in order invariant least fixed point logic is something like a logic for p-time, but there is a drawback because the syntax of order invariant least fixed point logic is not definable. So even for first order logic, it's not decidable if a given first order formula is order invariant on the class of all finite graphs. Okay, and if we look at not order invariance but ARP invariance, then Markovsky had shown that ARP invariant least fixed point logic precisely captures the complexity class P/poly. So that's all problems solvable by non-uniform circuit families of polynomial size. And how about first order instead of least fixed point logic? So what we also know is that ARP invariant first order logic precisely captures the graph properties and queries that belong to AC0. And here I look at non-uniform AC0. And AC0 is the class of all properties that can be checked by circuit families of constant depth and polynomial size. And if you just look at addition and multiplication invariant FO, you get an according characterization of uniform AC0. This here or the last one? The last one. Well, FO with bit predicate on strings, binary strings, precisely corresponds to D-log time uniform AC0. That's Immermann, Barrington, and so on. And then if you represent graphs by their adjacency matrix, then a graph property is invariant under isomorphism. And this precisely translates into invariant formulas. And bit predicate has the same power as addition and multiplication. So here you just look at Immermann's proof.
It's not specifically to plus times. It's any predicate that is coming. If you add the division or as long as it has a uniform definition, essentially.
As long as it's equivalent to the bit predicate.
Yeah.
So you can add the bit predicate instead of addition and multiplication. You can also add exponential function here or division or whatever, but you need the power of bit. Okay, and I already mentioned this drawback. The syntax of invariant logics is not decidable, so we can't use it as a logic in the strict formal sense. But we can use it as a means of defining queries and leave it to the user to make sure that the formulas he writes down are invariant, which is the same as we do for algorithms. When we look at an algorithm that should compute a graph property, we also trust the programmer that his algorithm really does compute a graph property and doesn't depend on the particular representation of the graph. Okay, but for the rest of the time, I want to look at non-expressibility results for, in particular, ARP invariant first-order logic. So we can use all kinds of numerical predicates. We still want to be able to show that specific queries or properties are not definable in this kind of logic. And there is quite a lot of things are known there already. So Rossmann's result from 2008, there he showed that the existence of a k-clique in a graph cannot be expressed by ARP invariant first order logic that uses only k over 4 variables. And from this he also obtained that the finite variable hierarchy of first order logic on finite graphs is infinite. So he didn't formulate his result in terms of ARP invariant FO, but in fact it is such a result. Then what else do we know? From work of Aitai, we know that reachability by paths of length f of n, so n is the size of the graph, f is an arbitrary unbounded function that you may choose, then Aitai tells you reachability by a path of length at most f of n is not definable in ARP invariant first order logic. And his proof even shows that this is true for particular graphs of bounded degree. And there is another result by Aitai showing that a graph having an even number of edges, this cannot be defined in ARP invariant existential monadic second order logic.
MSO1 or MSO2?
MSO1. Yeah.
Very important.
Yeah, that's important. You're right. And there are other results by Fagin, Stockmeyer, Wadi from somewhere the late 80s, which show that connectivity is not expressible in monadic existential second order logic if you have numerical predicates of some bounded degree. And there is also results of Thomas Schwentig in the same direction. Now what happens if you look at addition and multiplication invariant monadic, existential monadic second order logic? So there you can express connectivity of graphs because you have the bit predicate and a set of elements can be associated with a bit string of length n, and then by, well, guessing one set, you kind of guess a path of length n over log n, and then you can iterate this and get connectivity by addition and multiplication invariant existential monadic second order logic.
This has been shown? You can't mentioning it in passing, this is a non-result?
It's so I haven't read it anywhere, but I'm pretty sure that this is true. And maybe it implicitly follows from results by Grandjean and Olive. They looked at existential monadic second order logic and showed that there you can do everything that you can do in non-deterministic linear time on random access machines. And you can do connectivity in linear time. So I think somehow it follows from these results.
It's worth really writing, spelling it out, because the question is exactly of what is the limit of what we started with the taking et al. And inventing. Exactly. There was no clear limit to that inquiry. I don't think, at least I don't have a clear picture of what is the limit of that. So I think it's worth making it explicit.
Okay, so
yeah.
I'll write it down.
So are there any natural examples of properties that express with monadic existential second order logic, but not in plus times and variant?
So this reachability or connectivity is one example. We know that it's not expressible in ARP invariant first order logic from this result of itai in the middle. And if this idea that I just sketched works, and I'm pretty sure that it works, then it is expressible in addition and multiplication invariant existential monadic second order logic.
I was asking about monadic existential second order logic versus plus
versus full second order logic. So in some sense, full monadic second order logic corresponds to the linear time hierarchy. So I think you can find problems that are in there and not.
Monadic existential second order logic versus plus times and variant. So for example, parity is not an ARP invariant. So is there something natural in ARP invariant?
So monadic second order logic versus plus times invariant FO or plus times invariant MSO? MSO.
So how about just reachability over simple graphs?
Yeah. Right. That's not an existential monadic.
Yeah, but existential.
Yeah.
The question was about full monadic second order, or was it just existential? Yeah, okay, then that's an example. Thank you. Okay, so these are non-expressibility results. And I will add one more non-expressibility result, which is a kind of generic result for showing lots of other non-expressibility results. But what we look at is at local queries in the sense that Stephen already looked at, so I can very quickly go over this slide. So the distance between two vertices is the length of the shortest path between them, and then the R ball around a vertex is just the set of vertices of distance at most R. And one thing that I will use later on in the proof is I will also look at shells or spheres. And I say that the one sphere is exactly the set of vertices that have distance exactly 1 from vertex A. And the R neighborhood, Stephen already defined, so we won't do this. And also the neighborhood for the list of nodes instead of just a single node. So I will write, if A is a sequence of nodes, I will write NR of A for the R neighborhood around the sequence A of nodes. And I will use this calligraphic N for the induced substructure on this neighborhood together with constants for the centers of the neighborhoods. Now here's the important definition that I will work with during the next 20 minutes. So if you have a k-array graph query and some function f from natural numbers to natural numbers, then this query is called f of n local if there is, well, some number n0 such that for all large enough n, well, for all numbers n bigger than n0, and every graph with exactly n vertices, the following is true. Whenever I have two k-tuples A and B of nodes, and their f of n neighborhoods are isomorphic, then the query doesn't distinguish between the two tuples. So this f of n local, the f of n refers to the radius of the neighborhoods that I consider. And whenever two tuples A and B have isomorphic f of n neighborhoods, then they either both belong to the query result or they both don't belong to the query result. So the graph has to be of sufficient size, and the radius depends on the size of the graph. Now, what is known for this notion of f of n locality? So there is a theorem by Martin Grohe and Thomas Schwentig, and they showed whenever you have a query that can be expressed by order invariant first order logic, then there is some constant c, depending on the query, such that the query is C local. And C local in the sense that Stephen already considered. C local means whenever you have two tuples and their C neighborhoods are isomorphic, then these two tuples are not distinguished by the query. Now there is an open question, which is still open. The question is addition invariant FO C local in the same sense? So here you just look at order invariant first order logic, but what happens if you add addition in an invariant way? And there we don't know if it's local with respect to constant locality radius or not. But what we do know, and that's a joint result with Matt Anderson, Dieter van Melkebeek, and Luc Ségouffin from last year, we do know that we have locality with respect to a polylogarithmic locality radius. So the theorem says for every query Q that is expressible in ARP invariant first order logic, there is a number C that depends on the query, such that the query is log n to the C local. So whenever two tuples have the same log n to the C neighborhood, then they cannot be distinguished by the query. And here we really use ARP invariant first order logic, so you can have some undecidable numerical predicates that are used by the formula, but still you won't be able to look farther than just a locality radius log n to the C. And what we also know is that this locality radius is tight. So we know that for every fixed number d, we can define an invariant first order formula that just uses addition and multiplication that is not log n to the d local. But it is log n to the C local for some number C that depends on the query. Okay, and I want to show you the proof of this theorem. And that requires a bit of work. And before we do this work, let's have a quick reminder of what such locality results are good for. So I can use them for showing that all kinds of queries are not expressible in the logic. And the standard textbook example is reachability. So the reachability query that associates with the graph the set of all tuples of nodes that are reachable. So in a way that there is a directed path from the first to the second element in the tuple. How about this query? You look at two big circles. And so each of these circles contains n over 2 elements. And we can see that, well, the reachability query is not n over 5 local on this graph here. And our locality theorem tells us that if it was expressed by ARP invariant first order logic, then it would be log n, so polylog n local. Here it is not even n over 5 local. And this means this reachability query cannot be expressed in ARP invariant first order logic. And in the same way, you can prove non-expressibility for lots of other examples. And you can find all these in textbooks, like the query asking if node x lies on a cycle, or if node x belongs to a connected component that is acyclic, or if node x is reachable from a node that belongs to a triangle, or if nodes x and y have exactly the same distance to node z. All this you can show non-expressible in ARP invariant first order logic by just using this polylog n locality result. Okay, so how do we prove it? I want to show that every query expressible by ARP invariant FO is log n to the C local for some constant C. So the idea is, well, take a query Q expressible by ARP invariant first order logic. What we know is ARP invariant first order logic precisely corresponds to non-uniform AC0. So what we know is Q can be computed by an AC0 circuit family. Let's call this C. And now assume that Q is not log n to the C local for any C. And what we will do is we will modify this circuit family in such a way that we get a circuit family that computes parity. So parity means you get as input a bit string and you want to know if the number of ones occurring in this bit string is even. And well, what we know from Hastert and post-Saxe-Sipser and so on, that parity cannot be computed by an AC0 circuit family. So that will be the map that we are going to take.
Observe different reference.
So in the end, we really use Hastert's stronger bounds and not the post-Saxe-Sipser. So this here is a bit of cheating. I won't show that parity would be an AC0. I would, for a particular input size, give a circuit that's too small for Hastert's lower bounds. Okay, so how do we do the proof? And there I have to be a bit more precise in the way that ARP invariant FO corresponds to AC0. So how do we represent graphs or graph queries as inputs for AC0 circuits? That's what happens on this slide. So we represent a graph G by a bit string. I call it beta of G, that corresponds to an adjacency matrix of G. So you take just the rows of the matrix, you put one after the other, and that's the bit string. And for expressing a unary query, well, what our circuit should do is, given a graph and a node, check if the node is in the query result for the graph. So we also have to, we give the adjacency matrix as input to the circuit, and also an encoding of the node that we are interested in. And there we will encode a node A as a bit string beta of A, which has lots of zeros and just 1, 1. And this 1 will be at the position I, if and only if row and column I of the adjacency matrix represents my node A that I'm interested in. Okay, and then I say rep of G and A is the set of all bit strings that represent the graph G together with the node A. Why do I get a set? Well, because I have lots of equivalent adjacency matrices. So every way for embedding the nodes of the graph into the numbers 1 up to n, which are the rows and the columns of the adjacency matrix, for every such way we get one representation of this graph together with the node. So we have up to n faculty bit strings in there. And now a unary graph query Q of x is computed by a circuit family C. So circuit family means that for each input length n, I get a circuit Cn. If the following is true, for every graph G and every node of the graph, and every bit string gamma that represents the graph together with the node, we have that the circuit, well, for the according bit string length, accepts the bit string if and only if the node belongs to the query result. So the invariance of our formula is reflected in this thing here, saying that no matter how the graph is represented, the circuit must do the same with this. Okay, and now we know from Ibermann that a unary graph query Qx is definable in ARP invariant first order logic if and only if it's computed, in this sense here, by a circuit family of constant depth and polynomial size. So now we want to prove this locality result. So let Q of x be a unary graph query, expressible in ARP invariant FO. And we know that there is a circuit family of constant depth, let's say D is the depth, and polynomial size, let's say P of n is the size, which computes Q. And here is again what this means for every graph, every node, and every representative for the graph and the node. The node belongs to the query result if and only if the circuits accepts the representative. Okay, now we assume that our query is not local in the way we want it to be local. So assume that Q of x is not log n to the c local for any constant c. What does this mean? This means for every c that you might choose in the exponent, and for every number n0, there exists a number n bigger than n0 and a graph G with n nodes and two nodes A and B, such that the neighborhoods of A and B are isomorphic, but A is in the query result and B isn't. And what is the radius of the neighborhoods? That's the number m, which is exactly log n to the c. So here I just plug in the definition of the locality. So we have this situation. And to make things a bit simpler, we, in the remainder of this talk, only consider the special case where the distance between A and B is big, so bigger than 2m, which means that the two m neighborhoods do not intersect or do not connect to each other. But now the key lemma that we prove is this one, saying that if I have exactly this situation here, so if I have a number m, a graph G, two vertices A and B of the graph, such that their m neighborhoods are isomorphic and they are far away from each other, so their m neighborhoods do not intersect. And if we have a circuit C that accepts all strings that represent G and A, and that rejects all strings that represent G and B, so that's exactly the situation we have here, because A belongs to the query result and B doesn't. Then our lemma says there is a circuit C tilde of the same size and depth as the original circuit, and this circuit C tilde computes parity on m bits. So m is the radius of the neighborhoods. And I will show you how to prove this key lemma in a minute. Let's just finish the proof. So here we really use Hastad's lower bound, saying for any particular m, there exist constants L and m0, such that for all m bigger than m0, no circuit of depth d and this size, that's 2 to the L times m to the 1 over d minus 1, computes parity on m bits. So this here is more than polynomial, it's something, well, where m is in the exponent. Now how do we get the contradiction? Our key lemma says there exists a circuit that computes parity on m bits. And the circuit has depth d, which is the depth of the original circuit C that we had in the beginning, and has size polynomial in n, p of n. And now what is this here? 2 to the L times m to the 1 over d minus 1. So m is log n to the c. We choose a large enough c, like 2d. Then we have here L times log n to the 2d over d minus 1, which is 2 to the L times log n square, and that's n to the L log n, and that's bigger than any fixed polynomial. So there we have our contradiction. So everything we still have to do is show this lemma here, which is a kind of reduction. We reduce the situation violating this locality to circuit computing parity. So how does this work? So here is the statement of the lemma once again. So we want to compute parity on m bits. So let's consider a bit string of length n, of length m, whose parity we want to compute. And what do we know? We have this graph. So this should be the graph we have. This graph is fixed. And we have two nodes, A and B. And we know that their M neighborhoods are disjoint and they are isomorphic. So this here is isomorphic to that here. And let pi be an isomorphism. Now what we do is, whenever in our bit string at position I there is the bit 1, then we swap the ith shell around A with the ith shell around B. So what does this mean? Let's look at this. So let's say this edge here goes from the ith shell around B to the I plus first shell around B. And since both neighborhoods are isomorphic, we here have nodes U and V where you have the edge, and at the isomorphic image you also have the edge. And what you do is, if your ith input bit is 1, then you just swap the edges. So what does this swapping mean? Since everything is isomorphic here, what you do is you just, well, now I just, well, move this from left to right to remove the crossing here. And we have swapped the roles of A and B here. And so the picture is like this. Now, if you do this for every position of your bit string, what do you get? Well, for every position where you have a 1, you have swapped things. So if you have swapped for an even number of times, then the role of A is still the role of A. If you have swapped for an odd number of times, the role of A and B have interchanged. So what you get is, by doing this swapping, you get a graph GW. Well, that depends on this input string W, which is isomorphic to the original graph. And you know that if the number of 1s is even, then node A in GW plays the same role as node A in G. And if the number of 1s is odd, so we have swapped for an odd number of times, the role of A is the same as the role of B in the original graph. Okay. And what do we know? We know that our given circuit that we are given here in the assumption of the lemma, that this circuit distinguishes between GA and GB. So
don't you need the last, to make sure that the last level you don't swap? Because otherwise you break the isomorphism.
So you swap between levels. So the M neighborhoods are isomorphic.
Oh, M.
And they are disjoint. So the distance is bigger than 2M. So everything fits here. Okay, now how can we modify our circuit so that when it reads the bit string W, it does the same thing as the original circuit does when it reads a representation of GW and A? How can we do that? So we just look into the circuit. So we consider our circuit C that computes the query for some fixed input string gamma which represents G and A. And now for all input bits that do not correspond to edges from shells of these neighborhoods, just fix them. And we are in a non-uniform setting, so we can just fix them. And for all edges or potential edges between spheres, let's look at the situation. You have here node U, and there node V, and pi of U and pi of V. So which potential edges do we have between the ith shell and the I plus first shell around A and B? So there could be an edge from U to V. We call this E on this slide. There could be an edge between the images, We call this E prime. And there could be edges for swapping, which are not there in the original graph. That's E tilde and E tilde prime. So that's what's defined here on this slide. And what does our circuit C have? It has input gates for each of these potential edges, saying if the edge is present or not. And, well, what do we know if Wi, so the ith input bit of our bit string, is 0? Then we just take these two edges if they are present in the original graph. So we exchange this input gate E for E and not Wi. And the same for the other edge for E prime. And if the ith bit is 1, then we take these edges here. And that's exactly what the formulas do here. And by just doing these modifications, we get our circuit C tilde, and the size and depth hasn't increased here. And this new circuit accepts the string W if and only if its parity is even. Okay. So we have seen the proof idea, or almost the entire proof for this locality. So what I told you is the proof for disjoint neighborhoods and unary queries. If you want to do this for unary queries and non-disjoint neighborhoods, you still have to do quite some work. But the basic ideas, the combinatorial ideas that you use there, use a similar reduction from circuit lower bounds plus the combinatorics that's already used in the Goethe-Universität paper. And then there is another big step to go from unary queries to k-ary queries. What we do there is, well, we show how to reduce the case of k-ary queries to the case of k-1 ary queries. That's also done in Goethe-Universität, but we have to do it in a completely different way, because they could use, so if a formula is order invariant on a big universe and you restrict attention to a subset of this universe, it's still order invariant. We don't have this with addition and multiplication invariance or ARP invariance. So there we have to do a kind of reduction that doesn't change the size of the universe. And that required some kind of work, but I won't show this in this talk here.
What happens if you just try to get something a little better? Let's say log n to the c, divided by log n. Would that then you plug it in into the hashed bound, it will destroy it?
I don't understand the
corresponding
question.
upper bound.
So if you go a bit bigger than log n, we have a matching bound. And I will show the example.
No, but the C and the D are not the same. So I think what Moshe said, it's still
This could be a big gap between them. So I'm asking whether you try to tighten it a little bit, for example.
Well,
just the questions if you plug it into this little calculation that you did at the end to still make it, super polynomial. It's possible to me that you can get something a bit tighter.
So you want to get log n to the c over
log n, for example.
Well, but if you, here we just say there is a c, then take a smaller c. But we can also precisely say what this c looks like. So this c corresponds to the alternation depth of your formula, of the quantifier. Okay, so let me quickly give you an idea of how this upper bound works, or how the lower bound works, showing that for every d there is an invariant formula that's not log n to the d local. So this query that shows this part b here states that, first of all, the graph has at most log n to the d plus 1 non-isolated vertices. And the second thing that the query does is it says that node x is reachable from a node that belongs to a triangle. And why is this query not log n to the d local? So let's look at this query. So take a triangle and a path, and let this be our node A. And let this here be log n to the d. And then take another path and a node B, and let this be log n to the d. And then you have an awful lot of isolated vertices that make sure that the size of the universe is n. Then, well, the log n to the d neighborhoods of both nodes are isomorphic, but, well, this here is reachable from a triangle and the other is not. Okay, so how can we express this query by addition and multiplication invariant first order logic? So for saying this here, that there are at most polylogarithmically many non-isolated vertices, we can use the polylog counting capability of first order logic. And for the second one, well, what we do here is we show that in graphs where there are only few non-isolated vertices, in such graphs, reachability by paths of length log n to the d plus 1, or in general, reachability can be expressed by addition and multiplication invariant first order logic. And how do we do this? So we can use here a lemma of Arnaud Durand and Clemens Lautemann and Malika Moore that says that with addition and multiplication, or the bit predicate, you can, if you're given a set of elements of polylogarithmic size, of elements between 0 and n minus 1, then in first order logic you can define a bijection which maps the ith smallest element in this set to the number I. So in this way you can associate or identify elements in a small enough set with an initial segment of natural numbers. And this way you can represent each non-isolated node. There are only polylogarithmically many non-isolated nodes. You can represent each such node by a small number, a number smaller than log n to the d plus 1. And this can be represented by a bit string of length d times log n. And then you can use big numbers, and their binary representation has length log n. So you can use a big number to encode a list of such small numbers. So by an arbitrary number smaller than n, its binary representation encodes a sequence of non-isolated vertices, and the sequence has length log n over c times log n. And this way you can express that there is a path from one vertex to another of length L of n at most. And you can iterate this for a couple of times to get a formula saying there is a path of length log n to the c at most.
Could you just look at the parity of the number of edges and non-isolated path and bring that whole? So you just look at the non-isolated complement of the graph and just look at the parity of the number of edges.
For expressing,
No, just as a formula for showing that you get.
okay, yeah, but that's not a query, that's a property. And for this Geismann locality, you need free variables.
We look at the parity of the number of edges in the connected component.
Yeah, but then you also have to
Exactly.
compute what the connected component is. Okay, so I have 2 more minutes for the final remarks. So what did we see in this talk? We looked at Geismann locality, and what do we know here from Goethe-Universität? We know that order invariant first order logic queries are Geismann local with respect to constant locality radius. From the result I just presented, we know that ARP invariant FO is Geismann local with respect to polylogarithmic locality radius. And there is an open question concerning addition invariant first order logic. So we know that it's with respect to polylogarithmic radius Geismann local, but is it with respect to constant radius?
What lower bounds do we know for parity for first order derivation? And that would be
I don't know.
That would be the starting point.
So I don't know specific lower bounds except for the ones that we have for. So there is this paper by Lynch who showed that FO with addition cannot count beyond a constant. But this counting beyond a constant is on special positions only, and so there I don't see how to really use this. But the conjecture here would be with addition invariant FO you just have a constant locality radius. But I have no idea of how to prove this, and I tried quite hard. Okay, how about Hanf locality? So that's the second kind of locality that Stephen mentioned in his talk. So I don't look at threshold Hanf locality, but at isomorphic Hanf locality. So what do we know here? Properties of strings or trees definable by order invariant first order logic are Hanf local with respect to constant locality radius. So that's shown by Benedict and Ségouffin. And what we can also show, that's in the same paper from 2011, that properties of strings definable by ARP invariant FO are Hanf local with respect to polylogarithmic locality radius. We believe that it's true for strings just the same, but we admittingly were too lazy to check all the details, since we are sure that at some point, so you can transfer the methods from strings to trees, that's what we believe, but at some point you will have to get essentially new ideas. So we thought somebody else should check these details, if at all. But the open question here is, do these results generalize from strings to arbitrary finite graphs? So Hanf locality for order invariant first order logic on finite graphs, I don't know. I would expect that it is, but I have no idea of how to prove this. And for ARP invariant FO on finite graphs. Okay, and there is one final question. So are there decidable characterizations of these logics? So is there a language, like the question, is there a language for p-time or for order invariant least fixed point logic? Is there a decidable characterization for order invariant first order logic? That should be easier to prove than proving whether there is a logic for p-time. So maybe it might be a good idea to look at this question to kind of learn with toy examples, which are still hard enough. And the same, of course, can be asked for addition invariant or addition and multiplication invariant first order logic.
By this you mean there is a syntax, not if the problem is all decidable.
No, decidable syntax.
Decidable syntax. So is there a logic in the strict formal sense for these formalisms? And what do we know here? Again, from Benedict Ségouffin, we know that on strings and trees, order invariant first order logic has no more expressive power than plain first order. So here, plain first order is such a characterization that I'm asking for. What we know about addition invariant first order logic is very little. We know that on finite colored sets, so no edges but just colors on a finite set, their addition invariant first order logic has exactly the same expressive power as first order logic enriched with modulo cardinality quantifiers. So you can express what you can express in first order logic, and you can say the size of the universe is even or odd or congruent 5 modulo 17. But just for the size of the universe, not for the size of the individual colors. Okay, and that's it. Thank you very much.
Is there a possibility there's also a locality result for ARP invariant EMSO?
So there is this result by Aitai for ARP invariant existential monadic second order logic, and he also showed it for the alternation hierarchy, that he gave properties that are expressible in sigma k but not in sigma k minus 1.
I think a proof can be modified to show locality for that for EMS or
Yeah, let's talk about this.
But you said
That
you
would
can
surprise me because
you can do
I said
reachability.
with addition and multiplication you can do reachability, but with order invariant first order logic, I think there might be a chance. With order invariant MSO, there might be a chance to
You said
show
arbitrary.
locality.
You said arbitrary.
With ARP invariant, I'm pretty sure that you get connectivity.
with
Or
EMS
reachability.
With invariant EMS.
I think you get reachability, but we would have to sit down and do the details. But I think the idea is pretty much the same as the idea I gave for this kind of reachability within FO, where most of your nodes are isolated.
Yeah.
So it looks like everything you showed would go through if for FO with modulo counting quantifiers, if you use Rasparov-Smolensky lower bounds instead. Is that true or?
Well, we don't.
Seems that you just use the lower bound as opposed to the
I-
searching level.
I just used the lower bound. That's true.
The bounds are
But
at the
we-
same time. So
Yeah, that's true.
okay.
Could you go back to you had the list of problems in the first half of the talk that you are getting with the same method? Forget what slide it was. That were not ARP invariant.
So you
Yeah.
meant this, or
No, you had the list of other
where you
properties.
use locality for
Yeah. Yeah.
this here?
So this reminds me, there was this old paper of Kosmadakis from Fox 84 or something, where he proved non-expressibility in existential monadic SO by having one basic property and then having some very simple reductions. So do you have some very simple reductions that, rather than every time, or are these proof that using it?
So I believe that all this had been known before.
Yeah,
so,
but I'm
so
saying, can you-
locality is just a nice tool for easily seeing that these are not expressible. But I think if you use the lower bound on parity and do the standard trick by Gurevich and that's in the textbooks, you can do something like, you get a bit string and define a graph on it, which is cyclic or not, depending on whether the number of ones is even or
So
not.
let me rephrase it. Are there simple reductions under which ARP invariant are closed?
Order.
First order?
First order, just first order is enough, right? But
I think in all these cases, I think these are all first order.
all first order reductions, I think that's.
So, but I think Nicole's point is that here you don't need any reductions. It's almost direct to find to see that this is local. This is local. Local. Just look at it.
No. But before, you could do what she's saying, that you could reduce all of them to parity.
Yeah, those
Yeah,
reductions.
but
And this reduction of first order
That's
reduction.
exactly.
so I don't see this locality result as something that gives us new non-expressibility results, but
that's really
rather
what
it tells us something about the expressive weakness of this query language. Or it gives you a structural property of ARP invariant FO.
So the degree of the polylog, is it linear in the alternation
Yeah.
depth?
Yeah, I think it's the alternation depth plus minus 1. Because when you take the formula, translate it into the circuit, you get a depth associated with the alternation depth. And then that's almost the C that we take. So I took, in the end of this proof, I took 2 times the depth, but it suffices to take depth plus 1 to get the same contradiction.
And what's the alternation depth of the formula you get from that construction?
I have no idea.
Sam?
I just had a question on the polylog depth counting. Do you have like a citation for who did that originally or in this setting? Because it's similar to things in bounded arithmetic, so I'm just wondering.
And I think it's difficult to tell who did that first. So this polylogarithmic counting capability, there is this paper by Arnaud and Clemens and Malika they summarize things, and they also give a quite good record on the history. So people from bounded arithmetic had known this, and people from circuit complexity had known this, and then people from logic in some sense translated it from circuits to logic, and this paper that I cited was way later, but I like it quite a bit because it proves things purely in logical means.
Right. And the and this mapping to a small interval is based just directly on the polylog counting, is that correct?
It's based on similar ideas, but it's quite some effort to get it. So for logarithmic size, it's rather easy, but for polylog size of the sets, you really have to do some work there. And
it's a kind of divide and conquer kind of argument.
Well, the expert is here.
No, okay. Well, okay, we'll take it offline.
Yeah, let's take it offline. And this is the last talk of the workshop. So before we let's thank Nicole again.